Good morning, everybody. Welcome to AtCoder Beginner Contest 173. I'll be competing, showing my thought process through the contest. And at the end, I'll go over all the solutions. So if you're interested in that, you can skip to the end. Assuming I solve all the problems, of course. It's a shorter contest than usual, so that might not happen, but we'll see. Or shorter contest than Code Forces, I guess. ABCs are always 120 or 100 minutes. So good luck, have fun to everybody competing.
I don't know what project to prepare.
Oh. Alright, so we will buy a product for N yen. If we only use this many yen bills to pay, how much change will we receive? So it's this number mod 1,000. Or I guess negative that number mod 1,000. How big can it get? Not that big. Alright, so this is just, negative n mod 1,000 plus 1,000 mod 1,000. And that should be it. And then if I remember correctly, they want you to call this main.java before you submit. Yeah. I don't even run samples. RTE. That's interesting. Did I ever print the answer? Because it's one test case. Alright. Very good. And that should be fine. I guess I don't have my program for AtCoder yet. Okay, got it. Problem B, you're participating in a programming contest called this thing. He's just submitted his code to problem A. The problem has n test cases. For each test case, he will be given a string represented by the verdict. Find the number of test cases in which the verdict is each of these things. Oh man, it's kind of ugly. It's not a very interesting problem at all, I think. But we can solve it. Yeah, okay. Are these in? They're not in order. AC, then the answer, then TLE, and then RTE. The four, just RE. These are the four verdicts. Okay, so now if next dot equals ignore case AC, then A at 0 plus plus, else if it's equal to wrong answer, then that's position 1, and then we'll do these other two positions as well. So then this is TLE, and the last one is runtime error. Let's run this just to make sure I spelled everything right. AC3, wrong answer 1, TLE 2, awesome. needs to be main. Looks good. H and V. We've got a grid of H rows and W columns of squares. The color of the square in the ith row from the top, jth row from the left, jth column from the left is given to you. All right, we need to choose some number of rows, possibly 0, and some number of columns. Then paint all squares in the chosen rows, or paint red all squares in the chosen rows and all squares in the chosen columns. How many choices of rows and columns results in exactly k black squares remaining after the operation? It's very small, so we just brute force it. It is incredibly boring, but we'll do it anyway. I guess it's probably H first. This is our board. So we'll read in all of the characters in this line, fill in our board. All right, so now we'll try all possible masks. So for int mask from 0 to 1 to the width plus height. Then what we need to do is we need to check how many squares work for this. So now we have, we're going to go through all positions in the grid. So now if board at x, y, if it wasn't a black square initially, what character means black? So if it's not equal to this, then we can skip it. Or if the x or the y is blacked out. So if mask and 1 left shift x, or it has the 1 left shift width plus y, has either of these bits on, then, come on, if this is not equal to 0, so many parentheses, then we'll have painted it red. 1 left shift x, 1 left shift with plus y, no. Wait, I guess I need one more. Okay, that's not equal to 0, continue. Otherwise we need like a current count. So this is going to be the number of black squares, and then if count is equal to k, then we can increment our answer. And we just print our answer at the end. So basically we're iterating through all combinations of rows. I think that's good enough. So you have a bunch of players. The friendliness of each player is given to you. The end players will arrive at the place one by one in some order. To make sure no one gets lost, you've set the following rule. Any player who has already arrived should form a circle. The player who just arrived should cut into the circle somewhere. Comfort of the smaller of the friendliness of the clockwise adjacent player. Oh, so like you have a circle, you insert yourself into the circle, and then you get the smaller of the two. Like whichever one's least friendly is how much friendliness pellets you get. I see. Do we get to choose the order or something? Yes. Well, someone's gonna have to get 0 points, right? So the first person who comes gets nothing. And then after that, initially you have an empty circle. So the first person gets 0. If we put the biggest person, that's probably helpful. So we can put like the max. Then we have an empty circle. Then we can put the second max. So this will be like second max. And then we'll get like plus max. Then the next person we insert will get plus second max. Then the next person we insert will get plus second max. And then if we want to, we could insert, this could be the third max and fourth max, fifth and sixth. Or that's not how it would work really. So now you have to choose who these people would be. So I guess let's just consider the greedy. So this is 3 and this is 4. So now we'd have plus 3 for this. So this would be 5, 6, 7, 8 maybe. Plus 3 plus 3. Then plus 4 plus 4. Perhaps like this, plus 5 plus 5. Alright, so is this going to be optimal? It doesn't look like it. Because we've only included this max once, we could include it more. No, that's not true. The max you can only include once. Yeah, the biggest number you can only have, it's one time, because if you have like the biggest number and some other number, whenever you insert it in, you'll never get points for the biggest number. So we can't do better than this for the biggest number. For any other number, you could include it more than twice, but not really. The second max, for instance, you can only include it twice because it's the second max. Because if you have the biggest number here and the second biggest number here, if you insert 2 numbers here, in order to include it another time, you would need at least 2 of these to be bigger than it. And that's not going to happen. So you know this second max is included an optimal number of times. And then I think same thing for the third. If you have this third max, the first 5 things you can only have, like you can have this one for the first, then these two for the second two, but then you only have 2 more positions for this 3, and after that everything's going to be smaller than your 3. So I think that's just, oops, I think that's just the answer. Good. Let's implement it. So we've got our array, and now we just need to, I guess, make the final answer. So I'm just going to look at this pattern that I have and build the pattern into this array list first. Now we can look at the first n elements, or the first n minus 1 elements, because those are what we'll get points for. I could also have easily started at 1 here, and that would work as well. That should be your answer. Okay, sounds plausible. Looks good. Since I've already, to myself at least, proven that it's correct, I think I'm just going to move on. Multiplication 4. Given n integers, we need to choose exactly k of these elements. Find the maximum possible product of the chosen elements. Is that just not the product of the biggest k of them? Surely it is. Unless they're negative. There's the rub. Then print the maximum possible product under mod. All right. So I see. There are a couple cases. Let's case it out so we don't forget. So if there are any zeros, then we can make 0. If there, magic word. In other cases, we can have, like, we have a bunch of, so we'll have some set of positive numbers and some set of negative numbers. And if possible, we would like to take an even number of these negative numbers so that the sign cancels out and the product is positive. It can be n. Yeah, okay, so the next concern will be if, oh wait, what if the product is negative? Yeah, maximum product is -6, okay. Yeah. So if k is equal to n, then we have our answer. Otherwise, we have some choice. If they're all negative, then we have our answer. Or I guess we have two candidate answers, which depend on whether k is even or odd. So we either want like the biggest group or we want the smallest group by absolute value. If they're not all negative and we can remove at least one negative, then we can choose the sign of the answer. So in this case, we know the answer will be somewhat big. So then we can just pick them like in a smart way, like pick by absolute value. All right, so I think that's the solution that I'm gonna go forward with. Let's implement it. So our mod starts as 10 to the 9 plus 7. Well, it's not really starts, it's always that. That's how we multiply two numbers. Okay, and okay, so now we need our array. And now if k is equal to n, well then we have to print everything, right? So then multiply all the numbers together and print the product. And now return, I guess, because we don't want to think about that case anymore. Okay, so now if all of the numbers are negative, we need to consider that as well. So we'll count 0 as positive for simplicity, just like a really small positive number. So if we don't have a positive, then what we want to do depends on k. So if k mod 2 is equal to 0, then the answer is positive. Otherwise, the answer is negative. So if the answer is positive, then we want to well, in either case, we'll have a product, and we can print the product at the end. So then prod equals mul prod to a at n minus 1 minus I. So we'll multiply, if it's positive, we want to multiply all the big numbers together. Oh, I suppose if it's sorted, oh, we should sort this. Yeah, so then I guess the big numbers would be at the beginning. And then if it's negative, then we want the numbers closest to 0. Those will be the numbers at the end of the array. Good. So we no longer need the curly braces, but I'll keep them because it looks better, I think, with the comments. And then Awesome. So now I'll return as well. So now this is the last case in which we can choose whether we want it to be positive or negative. So we don't want to take the last negative if that will give us the wrong parity. So we need to know how many negatives there are. All right, so we have that. So now we should probably sort it by absolute value, right? So we make our array list of integers. We just need to sort this by return compare math.abs a to math.abs b. I'll return an int. Good. So we sort them by absolute value. I guess let's sort them in decreasing order of absolute value. So now the most profitable ones come first. So now we need, what is this, sort abs of a again, now it's sorted by absolute value. So 4 into I in a. If n negs is equal to 1, so if this is the last one, and k mod, or how many? So we have our answer. At the end, we'll print the answer. What about this? So, okay, so if the number of negatives is equal to 1 and not positive, that means and I guess we're currently positive, then we need to continue because we can't take it. Otherwise it will be negative forever. If n negs is equal to 1, and this is the last, okay, what do we want? We want, if we're not positive, and, well, there are two cases, right? If I is less than 0, or it's not. So if it's less than 0, we do this. If it's positive, then if our current product isn't positive, and I is positive, and k is equal to 1, then we need to continue. Because if we take this, then we're out of numbers, so we can no longer make our sum or our product positive again. If it's negative, in all other cases, we just want to take it. Yeah. If it's negative, then we only don't want to take it if, like, this is the last thing, if this is the last negative. Otherwise, we'll take it, and then we'll take the matching negative later, I think. Or no, that's not true. Yeah, I see. Smart. Yeah, this approach doesn't work. Alright, cool. So we can fix that pretty easily though. So we're gonna need an array of positive things and negative things. Let's go back to the drawing board here. We're gonna need positive and negatives. It doesn't work because, like, you have to make decisions. Like, I'm finding like the lexicographically biggest one, but I don't want that, like, because like 8 times 1 is less than 4 times 4. So that would give me the wrong answer. Alright, that's fine. So if we have some positive numbers here, maybe we got like 1, 3, 5, 7, and we have -4, -2, or let's sort them. -4, -5, -10. So initially we'll take as many of these as possible, but the parity has to be right. And we'll take no negatives. Then we can take 2 negatives and erase these 2. Then we can maybe take 2 more negatives and then erase these 2. And we'll do that forever. So what we need is we need a mod inverse. I'm not going to explain exactly how this works because I have a video on it. It's division under mod. It's algorithms dead, I think episode 1. Otherwise, so this is like how we do FastPal. If we take something to the mod minus 2 power, that will give us the modulo inverse of it. Alright, so let's make well, we don't know how many. I guess that was non-harmful. Alright, so int array positives, new int array n minus n negs, negs equals new int array n negs, and then for plus new index equals 0. So if a at I is greater than or equal to 0, then positive at p index plus plus is going to be equal to a at I. Otherwise, the negatives at p or negative index plus plus is equal to a at I. So now we have our list of positive numbers and negative numbers. And we can make this a little bit better by sorting them here. So let's do that. So let's make this initially n negs minus 1. And let's make this n negatives minus minus. So now we have our positive numbers sorted in increasing order. Ooh, I did that backwards, didn't I? Yeah, we should probably make this increasing and the positive one decreasing. That way our good numbers come first. All right, good. So now we need our current product. So this is, we know we can like make it positive. So we want to include up to k things in the positive group. Yeah, okay. Well, the real question is how many do we want to include? I guess let's just include up to k. So for each of these things, then we want, well, it's long ans, right? Then ans equals multiply answer by positive at I. So now if positive at, or if positive dot length is less than k, and positive dot length mod k is not equal to mod 2, not equal to k mod 2, then this means that if we include all of the positives, we'll have an odd number of negatives. So then ans equals multiply ans by the mod inverse. So we want to divide out this number, positive at positive index minus minus. And now we want to, yeah, okay, that's fine. So now for int I equals 0, or I guess I equals positive dot length minus positive dot length. Well, hang on. I is equal to 0. I is less than k minus positive index plus 1. I guess less than or equal to this. Well, let's do the math. Okay. K is how many things we need. The top has positive index plus 1 things. All right. So these are the things we need to include in the negative half. So ans equals multiply ans by negative at I. All right, cool. So now for int I equals 0, I plus 1, or I guess this is negative index, right? So we better include an odd number of those. Oh, we have this issue that we're including zeros. So we won't be able to divide them out. Interesting. Yeah, that's kind of funny. I could just do this with prefix products. That would be much easier. Yeah. Well, okay, oh well. We'll fix that in a minute. So we want to include positive at 0 to positive at positive index, I think. All right, well, I guess let's just make these prefix sums now. What am I doing here? So I read in, yeah. So this feeds in the positives and the negatives. Wait a second. What am I doing here? This doesn't actually give me the answer. Yeah, this is unhelpful. Because like I'm finding the maximum under mod. So I can't actually compare these. Is this like actually hard or not? It's not. Let's look at problem F then. You're given a tree with n vertices and n minus 1 edges, respectively numbered 1 to n and 1 to n minus 1. This edge connects these two vertices. For integers L and R, let us define a function below. Let S be the set of vertices numbered L through R. So we take some continuous range of vertices. This represents the number of connected components in the subgraph formed only by the vertex set S and the edges whose endpoints belong to S. Both of whose endpoints or either of whose endpoints? Presumably both. Do we have a bunch of queries or something? Oh wait, what's this question? For all pairs, find this and now find the sum. Do we print it? I guess the answer is at most n cubed, right? So we don't need a mod. So it's a fun question. I think I'm kind of enjoying that. Let's look at if we have. Why am I drawing an array? It's a tree. So it's helpful to consider only edges, I think. Yeah, or maybe it's not. So, well, like let's imagine each node is going to be a +1 component. And then each edge, if it's included, will be a -1. Then the total number of, if our graph looks like this is going to be 1, 2, 3, 4, 5, -1. So this will be a total of 4 components. So that's right. So now we just need to figure out how many times is a node included and how many times is an edge included. Right? I think that's right. Yeah, so I guess let's look at this. So 1, 3, 2. So a 1 gets included how many choices do we have here, and how many choices do we have here. So this will be, well, this will be 1. This will be 3. So this gets included 3 times. And then this edge will get included. You've got to have the 1 here, the 3 here, and now you have 1 choice over here and 3 choices over here. So this is for your edge. So this will be a -1. This will be -2. This will be +3. This will be +3 for the same reason. And then the 2 was interesting. So you have 2 choices here, 2 choices here. So this will be +4. So this should add up to 7, and it does. Awesome. So this should be a very easy problem. So let's implement that really quickly. It's a very interesting problem too, though. It's a good problem. I actually really like this one. Usually, I don't know, ABC problems sometimes I find uninteresting, but this was a quite cool one. It's very clever. Good observations. I mean, I also solved it quick, so it might be a bit biased, but yes. So what we need some math stuff. Let's copy our exponents and mod inverse, and also multiply. We want all of those as well. Ooh. No, we don't need factorials. Yeah, we don't need any of this really. Never mind, we don't need this at all. Okay. So the answer is initially going to be 0. And now for each node, we know how many times we will include it. All right. Ants plus equals ants times, or what's going to be I plus 1. That's how many left choices you have. How many choices do you have on your right? You have n minus I. So this counts all the nodes. Awesome. So now we need to look at all of the edges. They're 1 indexed. So ants minus equals the min, that plus 1 times n minus the max. I think that should be fine. Yeah, I'm pretty confident if those are right, this will be right. And if that's right, the problem's right. Very clever. Very clever indeed. All right, so how do we do this E now? Seems very difficult. Oh, maybe not. Yeah, okay, this isn't actually that hard. This isn't that hard because we can see, yeah, we just need to, it's easy to mess up, I guess. Okay. So we have to be careful with like comparisons because we have to do all of our comparisons before modding. Because after we do mod, we lose information about what those comparisons are. But if we have something like really all we need to compare, we'll have a bunch of positive numbers. We also have a bunch of negative numbers. And we're gonna take like, let's say this is like the bigger, this is the small for both of them. Like when I say big negative, I mean more negative, farther away from 0, bigger absolute value. So we're gonna take some prefix of these. We're also gonna take some prefix of these. And then as long as we can delete these two and replace them with, let's say we take, let's say we initially start with no prefix. So what we want to consider doing is deleting these two and taking these two. And we want to do that as long as the product of these two is smaller than the product of these two. That's the goal. And then if it is, then we'll swap them and then we can continue. We can just evaluate whether this whole thing improves because that'll be bad. We also probably can't do the log trick. You can evaluate, like, the issue is that these numbers will get huge if you multiply them out. So you might be tempted to like try and solve this under log because then the log doesn't get huge. But you have to be very precise, and that seems like a difficult thing to do with doubles, even with long doubles in C++. Seems like you just have to know more than what you can ask a computer to do, like, feasibly. Okay, so I think this is fine. So we just have to be careful with our indices, and then we should be fine. But I think that means we can, like, there's not too much we need to do here. This mod inverse, I don't think is actually important. So wherever we're using that, and wherever we're using this POW, we need to rethink that solution idea. But this part's true. This part is also true. If we have no positives, we should be able to figure it out right away. If we know our answer is positive, we want the stuff close to 0. If we know our answer is negative, we want the stuff far away from 0. Okay, otherwise, we have at least one positive, and k is less than n, which means it's possible to do this correctly. Get all of our positives and all of our negatives. Okay. So let's let's pre-compute our positive and negative prefix sums. Alright, so we have these prefix sums. Now we can figure out some prefix in order 1, except we need to do that. Alright, so now where do our pointers start? Well, I guess we figure that out here, right? So int pos_cs equals k. Met.min pos. Well, okay, so here's the thing, right? so it's going to be positive index is going to be equal to k mod 2 plus math.min of the positive dot length minus 1, because we're adding minus k mod 2, because we're adding k mod 2 to it later, or k. Like, we don't want to take more than all of them. Or what is this really? This is k minus k mod 2. That's not right. There's no way that's right. Well, let's just do this and fix it in a minute. So it's okay. So negative index is going to be equal to k minus positive index. This is just n positive, right? That's how many positive things we have. And then the number of negative things we have is going to be equal to this. K minus n positive. Everything else is going to be negative. We'll do this out in a minute. So we have a bunch of positive things, a bunch of negative things. The issue is we might have an odd number of negative things. And if that's the case, we need one more negative thing. Because we have as many positives as possible, we can't add one more positive. Good. All right. So now we need to consider doing a bunch of trade-offs. So we can do a trade-off. So look at this picture. So this is n positives. This is n negatives. So while n negatives plus 2 is less than oh man, this is asking for disaster. Oof, I'm gonna have to be careful here. While this is less than n negatives, so well, how many I have plus 2 is less than or equal to, yeah, less than or equal to the number of negatives. And the number of positives I have is greater than or equal to 2. And also it's a good trade-off. How do we know if it's a good trade-off? If well, this should be pretty easy, I guess, right? So positive at n positive minus 1 times positive at n positive minus 2. If the positives is less than, is it less than or equal to? Does it matter? I don't think it matters. Yeah, it shouldn't matter. Less than negatives at n negative times negs at n negative plus 1. Lots of conditions. Okay. So while this is true, n positive plus equals 2 and negative plus equals 2 rather, should be a minus. So we take away 2 positives, add 2 negatives, as long as that's beneficial. And then at the end, I suppose I didn't even need the cumulative sums, right? So we want to print the positive cumulative sum at number of positives, and then the negative times the negative cumulative sum at n negatives. Okay, that's a lot of math, but I don't think that's going to be too big of an issue. Samples are not very good. Hello. What is going on here? All right, why is this 0? K is definitely not equal to n. Good. Okay, we have positives. Two, 1, -4, -3. That looks fine. Am I doing this wrong? Should be fine. That's my multiply. Just multiply the two things under mod. Fine. All right. Print two negatives. Yeah, that's fine. Good. Negative CS at n negatives. What a cyan move. Okay. I'm a silly goofball. Can't do cumulative sums. All right, let's try this again. 12. That looks right. That also looks right. That looks fine. Looking good. So probably not great penalty because I'm slow, but yeah, not the end of the world. Am I really gonna get dinged for this A? Come on, man. I didn't even pass test case 1. Oh well. A is a hard problem, what can I say? Yeah, so let's go over solutions then. Very good. Cool. So solution time. In problem A, now where did this come from? Is this just my clipboard? How do I get rid of that? Okay, good. Problem A, you buy something, and when you buy something for a certain price, you just pay like, you pay multiples of 1,000. So you're gonna pay like 1,000 times like some integer. So maybe like 1,000 times 7, you give them 7 $1,000 bills. And then they subtract out some number of change. So maybe they subtract out like a 900 something. Then when you finish, this is going to be like some number of 1,000. So maybe it's like 3,000 and 110 or $100 or something. So you could have not given them 3 more $1,000 bills, and you can just subtract that. So now the question is, what is this value? Like, what's the value of like 1,000 minus what they give you? So I guess the entire problem is implementation details, right? So you take negative that number, and then you want negative that number mod 1,000. But that's going to be negative, so to make it like positive, then you add 1,000 and mod by 1,000 again. In Python, I think you could just do the number mod 1,000, because I think in Python mods are positive, which makes sense, I guess. Like, this mod plus mod is a common thing that would be nice to have in general. Cool, yeah, so that's problem A. Problem B is one of the most boring problems I think I've ever seen, to be honest. I'm not a fan at all. It's kind of mega lame, but you just oh, there you go, look at that. you just read in, you count how many strings of each type there are. So it tests whether you can do string equality checks. And in Java, that's what this looks like. You can do equals, ignore case. I think you can also do equals. Yep, that's it. Then just count how many of each there are and print how many of each there are. There's nothing to talk about really for that problem. You just have to do it. Okay, cool. In this problem, you have a grid of characters. So you've got like some grid. And what you're going to do is you're going to delete all of the black spaces in some number of rows and also in some number of columns. You want to count how many ways there are to do that, so that the total number of black spaces remaining will be equal to 2. Or equal to k. The important part is that the number of rows and the number of columns is very small. So what we can do is we can, like, if we have some grid, it doesn't even matter what's in the grid too much really. We don't have to think about it really at all. We can just brute force maybe like which columns we delete. So maybe we delete maybe we have this bit mask, so this would correspond to, like, we have let me move this over a bit. There we go. So maybe this is our mask. And like, it should be pretty clear that this first half corresponds to this first half here. So we just delete this row and we delete these 2 columns. And after we do that, we want to see how many positions in the ones that are left over are like the hashtags, the pound signs, the octothorpes, sharp symbols. Anyway, you get the point. So you just look through the entire grid and see, okay, like this position is in a crossed off space, this position isn't an octothorpe, then this one is exactly what you want, so you add 1 to your counter, check if it's equal to k. You can do this with a, like, this is essentially checking all combinations, and you can check all combinations by counting in base 2. So you can increase your count, and this is like a bit mask, and then you can see for each bit, is it going to be on or off, stuff like that. Okay. Oh, that was problem C. Problem D. Yeah, okay, so problem D was pretty interesting actually. So in problem D, you've got like some circle, and you have a bunch of people who will enter the circle one by one. So initially you have someone, maybe it's like value 10 enters the circle, and now you can have someone else enter, and maybe that person's value is like 5, right? So now you have a 10 and a 5 in your circle. And not 10 choose 5, just a 10 to 5. But when the 5 enters, he's greeted by the 10. He's like, oh, how nice. So now you get 10 points for having the 10 person greet you. Now maybe somebody else comes in, maybe this is like an 8. And when the 8 comes in, he's greeted by the 10 and the 5, and the 10's like, oh, it's a very nice person. The 5's like, oh, it's an okay person. So he just assumes the worst, naturally, and he gives a bonus of 5. Because he sees the 10 and a 5 next to him, he'll get the 5 bonus. So a lot of people ask like how I think through this, and what I did is, like, in this case, for example, it should be pretty clear that we can do better. It would be better because, like, what this person's charisma is doesn't actually matter. It only matters how nice the people he sees are. So instead of having the 10 come first and then the 5, we could have the 10 come first and then the 8 and then the 5. And when we do that, then we get 10 points plus 8 points. So it's kind of like an exchange. We can trade out the 5 for the 8. And if we do that, we get an extra 3 points. So that's always a beneficial thing to do. Or it's not necessarily always, but it is in this case. So it seems that like maybe one approach that you might want to go down, one good solution idea might be we probably want to put the bigger numbers in first and then the smaller numbers in later. That seems like it might be helpful. So let's try and actually do that. If we have like, let's call the biggest number, let's say the biggest number is like a 10 and then 9 and then 8 and so on, just for simplicity. So you put your 10 in somewhere. Now, if you put your 9 in, you're going to get 10 points, right? So you'll get your plus 10. Cool. Now, when you put your plus 8 in, maybe you put your 8 here, or it's not plus 8, it's just your 8 person, then they're going to get plus 9 points because they're going to be next to the 9. There are a couple places you could put your 7. You could put it here, I guess, and then they would get 8 points. But you could also put it here, and when you put it here, they would get 9. So let's put it there. And then we get our plus 9 points again. Now we want to put the 6 in somewhere. Or wait, that was the 7, right? Yeah, so now we want to put the 6 in. We can put the 6 in here, right? If we put the 6 in here, we get 8 points. So we get this plus 8. We get a plus 8 again. Plus 7, plus 7. So you'll see this is kind of like the pattern that works out. Basically, the first number you can only get one copy of. And that's the best you can ever do because there's only one thing that you can get that from. The second number, these first 3 numbers, they can't, like they can all be equal to this because we have some way of doing it. But this fourth number, there's just no way to make it a 9. Like this fourth number has to be equal to this third best number. Because the first number we can use once, and this 9 we can use at most twice. We can use it by the 2 next biggest numbers, but then after we've used like this edge, after we've used this edge twice, right, we've put something between it on this side and between it on this side, then we have to use some other edge. That's got to connect the second biggest number to something smaller. And when it connects those two, that means the value is going to decrease, right? It's going to be smaller than the second biggest one, because the second biggest and the third biggest, the smaller of them is going to be the third biggest. So after we use this edge twice, then we're going to have to get to the third biggest, which is the 8. So now we can use this edge and we can use this edge. We can use each of them once because we only have one side of them. And you could also put the 7 here, but that would just be a worse move. And then we get our 2 8s, but then we can't have any more 8s. So you can prove that this is optimal. I guess that wasn't super formal, but I think it's pretty understandable why that's right. So then the TLDR is you've got this array. It's like 10, 9, 9, 8, 8, 7, 7. I just build this array, and then I take the first n-1 elements from it. N-1 because the first person doesn't get any bonus because there's nobody in the circle when he gets there. Awesome. Let's look at problem E. So this was actually the last one I solved. Was it a cool problem? I don't know. I don't really have a super strong opinion on it. I guess it was pretty cool. It was somewhat interesting. There were a lot of traps, I think. There were a lot of ways you could get it wrong. But the idea is you've got a bunch of numbers, and then you want to find, if you pick k of them, what's the biggest product you can have. So there are a couple cases. If k is equal to n, then obviously you have to pick everything. So then this is like totally forced. The next case that I special cased out is if you have all negatives, then there are kind of like 2 different possibilities. So if you've got like -1, -2, -3, -5, -12. Let's say k is equal to 3. If k is odd, then you know your product is going to be negative, which means you want it to be as close to 0 as possible. You can do that by picking the k items that are closest to 0. Those have the smallest, like the least negative product. And if k is even, like k is equal to 4, then you want to pick the k biggest elements because you know your product is going to be positive. And it's just like they were all positive numbers, right? Because if you pick 4 of them, your answer is going to be positive. So if you pick these, then you will you'll be fine. All right, very good. So now if we aren't forced to pick all of these things and we don't have all negatives, what that means is we can choose some positives and some negatives so that our sum is going to be positive or 0. Like let's imagine we have a bunch of numbers here and I'll write them in descending order so it's easier to think about. So maybe it's like 5, 3, 3, 2, 1, and 0. And then for negative numbers we have negative 4, negative 2, negative 1, negative 1. So when we have this, we'll always be able to pick, like maybe k is equal to 5. So we can pick these 3 numbers and these 2 numbers maybe, and I think that might be the optimal answer. It sure looks like it actually. But the important part is the product here is going to be positive. And same thing, if we just start with the first 5 elements, our product will be positive. Yeah. And then if we start with as many of these as possible, and then we like overflow into the negatives, what we can do is we can repeatedly subtract 2 positive numbers, subtract the smallest 2 positive numbers, and then add the 2 biggest negative numbers, or I guess I'll circle them. So we can add these 2. And if we do that, then our product stays positive, or it stays non-negative at least. So that's the idea. We start with as many positives as possible, and then we repeatedly subtract 2 positives out, and then add 2 negatives. And we want to keep doing this as long as our answer improves. As we subtract these out, then the amount that we subtract out becomes more and more valuable. So it hurts more and more to do that, because we're subtracting, or we're dividing out bigger and bigger numbers. So initially, like this 1 times 2 is pretty small, but eventually we'll be subtracting out 3 times 3, and then maybe if there are bigger numbers here, we'd be subtracting out really big numbers. So we want to avoid doing that. And then, or like basically it doesn't hurt as much, but it hurts more and more. And then the same thing kind of in reverse happens here. We get something pretty valuable, but then after that we'll get something less valuable, right? So this will give us 8. We'll be multiplying by 8. This will only give us 1. And then we'll have less over here and more over here. So as we do this exchange, this top row becomes like more important to keep, and the bottom row becomes less important to take from, which means there's some position where like the trade-off will no longer become necessary, but on either sides of that position it will definitely be helpful. So we could binary search this if we wanted to. We don't need to, we can just like take it one by one. And the important part is we only have to look at this change. We don't have to look at the actual product. All right, I think that's a good explanation. So yeah, so you compare the product of these 2 numbers to the product of these 2 numbers. If that helps you, then you move your pointers over to like that. Then you compare these 2 numbers to these 2 numbers. These are 9, the bottom ones are only 1, so that's not helpful, which means that's your final answer. Just multiplying all of these numbers together. Yeah. I think that's all I'm going to cover for that. I think that's all that's important. Intervals in a tree, man, I thought this was a really good problem. I really enjoyed it. You've got a bunch of nodes and edges on a tree. And what you're going to do is you've got, like, the nodes are numbered. So maybe it's like 1, 2, 3, 4, 5, 6, 7. The edges are also numbered. Wait, are the edges numbered? Oh yeah, I guess the edges are numbered too, but the edge numberings don't matter. And now the question is, if we only look at like nodes, well, this isn't the question, but if we only look at nodes for, well, that's a bad example. Let's look at nodes 2 to maybe if we look at like 1 to 3, If you look at nodes 1 to 3, the only nodes that are still there will be these nodes. So we have two different components. We've got this one here, and then we also have this one here. So we would add, like this will give us 2. And what we want to do is for all pairs of ranges, so like from 1 to 1, from 1 to 2, from 1 to 3, from 1 to 4, etc., all the way up to 1 to 7, we want to add up how many components there would be if we include all of these nodes. Then we want to do the same thing from 2 to 2, 2 to 3, all the way up to 2 to 7, and then we want to keep doing this all the way up to 7 to 7. Awesome. So, how much time's left in contest? 20 minutes? Sorry, it's fine. I won't upload it, obviously, until contest is over, but, yeah. So here's the observation. If we want to count the number of components in a tree, if we have any tree, if it has like 5 nodes, in order to connect this to make it a tree, we're going to need to use 4 edges. That should be pretty clear. You can just draw out a couple examples. The other thing is, every time we have an edge, we connect 2 components on a tree. A tree is something with 1 component. So, like 5 minus 4 needs to be equal to 1, because every time you connect 2 things, you subtract 1 from the number of components. So what we can do is, if we count, like let's say we've got some nodes and some edges, and maybe we know somehow that these are the nodes and these are the edges. Well, what we can do is we can count each node as like a +1, and we can count all of the edges as a -1. And now, of all of the things that are alive, what this tells us is the total sum will be equal to how many components there are. In this case, the sum is equal to 2, and there are 2 components. Why do we want to do this? It's very helpful because looking at it in this way makes everything independent. So we only care about how many times does this edge get counted over all test cases. We don't actually care about like components anymore, because those were interacting in a kind of confusing way. Now we can just only look at this -1, and answering just how many times does this edge contribute -1 is a much easier question. Okay, so now we have, well, let's look at nodes first. We also we want to see how many times does this node contribute a +1, right? So if, let's say there are, maybe 5 nodes. So you've got 1, 2, 3, 4, and 5. And let's say you're going to be node 4. The question is, how many ranges of nodes contain this node 4? Well, range 1 to 5 would, like 2 to 5 would, 2 to 4 would, there are a bunch of them that would. Let's look at like the left and the right endpoints of the range. So the left endpoint can be 1, it can be 2, it can be 3, or it can be 4. And then the right endpoint can be 4 or 5. And for any choice, since those are independent, for any left endpoint, we can choose any right endpoint. They're just going to be 4 left times the 2 different right. That'll give us 8 different possibilities. And that's pretty easy to count. So if this is index I, then the left is just going to be I plus 1. And then the right will be, assuming it's 0 based, the right will be n minus I. So that's how many ways there are to do it. Awesome. So that's how many times each node contributes. We just multiply all those for each node. Then let's look at each edge. So if we have some edge, maybe let's draw the nodes in back again. So maybe we have this edge that goes from 2 to 4. Connects these 2 nodes. Well, the only time this edge will be in the graph is if both node 2 and node 4 are simultaneously in the graph, which means the range has to be, it has to contain the range 2 to 4. So what left endpoints are there? Well, it has to be the has to be left of the 2, and the right endpoint has to be right of the 4. So we just have to look at the minimum of the two things here, and then the maximum of the two endpoints of each edge, and we can say how many times this edge included. So it winds up being actually like a really easy problem to implement. There you go. This is the entire code, super short, but still quite clever. Not obvious at first, and it's also not too mathy. I think like you don't have to go sit there with a sheet of paper doing equations, figuring stuff out for 10 minutes. You can just like think about it for a minute, realize that this nice observation about nodes and edges on a tree, and then straightforward from there, I think. Awesome. So that was this ABC. I thought the problems were pretty nice. I didn't like B at all. I thought B was quite silly. But I thought the rest of them were all very nice, especially for AtCoder round. Usually the ABCs tend to be just like a little lame. Nice job, William Lynn, for third place. I heard, well, can you see friends here? How do we do that? You can do 1,000 per page, the power. Oh my goodness. Geothermal, oh, you did get it. Bunch penalty though, that's fine. Where are we? Surely we're better than that, right? We're 75th, I think, 80th. Yeah, I guess we just, the penalty beat us. He was fast as usual. Who won? I don't know. Be true. Maybe an AtCoder guy. Not really a Code Forces man. Oh well. Hope you enjoyed the contest. I'll see you next week in the next AtCoder maybe, or I think Code Forces rounds are not for a bit. The next one's not for like 7 days. So yeah. Oh well. We'll see. Hope you enjoyed, and if you care about your AtCoder rating, hopefully that went up as well. Goodbye.